My RC car is somewhere out there. I cannot see it with the naked eye, so I have to use 20x zoom. And I'm controlling it with the PS5 controller over a custom LoRa radio link I built myself. Here is how I got here. This is the architecture of our control system. PS5 controller is connected to the phone over Bluetooth, and a React.js application uses gamepad APIs to read stick positions. This data is being sent to Raspberry Pico over WebSockets. Raspberry Pico runs a Wi-Fi endpoint, so the phone can be connected directly to Pico without internet or a router needed. So Pico checks those data and fires them over the LoRa module to the receiver side 20 times per second. On the receiver side, this data is being converted to PWM, so it controls direction and speed of the motor and both servos. In addition, once every 2 seconds, the model sends the quality of the radio link back so we can show them on our phone. And if the model hears nothing from the controller for a second, a failsafe is being triggered so we can stop the motor from running. We could totally eliminate the phone from here and connect the controller directly to Pico, but it's nice to have a screen so we can see what's going on with our radio link in real time. Boards on the controller and the model are the same. So this one will go on the model, and I upload the code to simply flip servos and motor once every couple of seconds, just to make sure everything works on the board itself. And there is a link in the description how this board is created. This is my old Android phone, and we're going to connect PlayStation controller to it as a first step. We just add it as a Bluetooth device, and we can see that the controller works as an input. Alright, and after the controller is connected to the phone, I have a React.js application which basically shows me the both sticks. And if I need to, I can move the values using the phone itself, which helps in case the controller is down. But I can also use the controller. So this is my speed, forward or backward, and it's around 0 when nothing happening. And this is for my turning. In addition, I have one more component here, which is the gear switch. And when I press the button, it changes. And all this data is being sent over the WebSocket to my server. Currently I run it on my computer, and I shared my screen on my iPad. So let me bring it here just to show how it looks like. And you can see that on the server side, I can manage my speed using a stick. So value from here travels through application and WebSocket, or my direction. And every time I click the button, my gear changes as well on both sides. And in addition, this script sends a telemetry back to the phone. So my phone shows this is a made up values, but nevertheless. Alright, so this is our final assembly. On this side, this is the model, and this is the controller. So we have here the receiver Pico with LoRa module, USB battery which will power all of this, 2 servos to control, one for steering, one for gear, and our motor which we can move forward or backwards with different speed. And on this side we have our phone for the telemetry, the center side Pico, another battery, although we can use the phone for the battery, and our controller. So let's power everything up. So we see the power is going and the LoRa is listening, and everything should be powered up on this side. Now we can power up this unit. And let's connect to the Wi-Fi. And we have Wi-Fi without internet here. Now if I go to my application, that resetted the gear, and the rest of the stuff. And we can see there are metrics coming from. So now as soon as I touch any buttons here, the controls from the controller will override whatever is here. So let me just do that. And I'm going to press this button to update the gear. So look. This is our steering. And this is our speed for the motor. My bad. Alright, and this is all the 3D printed elements for the car. The difference with the previous chassis is this is the old wheels and this is the new ones. This is for the front and much larger for the back. And the goal here is to be able to drive a little bit faster, because we're using this motor, which is cheap, slow, only 48 rotations per minute. And we're going to mount the PCB, and the battery will go under. All the elements to mount this battery, this USB battery, 5000 milliamp. So 2 amp, it should give us 2.5 hours of driving. And it goes here and then goes on top. And that's the final product. The battery, the PCB with an antenna, and it just simply goes on top of the chassis. And that's our car. The rest is add the power from here to the PCB, connect the servos to the plugs, and same for the motor. And we are ready to go. The plan for the outdoor testing is basically drive the car far away until signal to noise ratio has become close to 0. And then just drive it back. And this is our test rig. The phone shows the telemetry for the signal. You can see that signal to noise ratio is close to 0, at least fluctuates there. The phone is zoomed in 20x to show the model 200 meters away. And the PCB is on the tripod as well. We are -77 and 12 on the noise pretty much, and -90 on the strength. Okay. And here we are past 200 meters, and our telemetry shows a connection is a bit spotty. So pretty much for this antenna placement, that's the greatest distance we can get reliably. And I checked the distance with this rangefinder, and the distance is, to be exact, 211 meters. And that's pretty much all for this experiment. And next time I'm going to put all this electronics on a board to see how the radio behaves over the water.